Black holes are among the most fascinating objects in the universe. These enigmatic entities have captured the imagination of scientists and the public alike for decades. Their mysterious nature and the extreme conditions they create make them a subject of endless curiosity and study. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. This boundary, known as the event horizon, marks the point of no return. Once something crosses this threshold, it is inevitably pulled into the black hole's depths. Black holes form when massive stars collapse at the end of their lives. This process often involves a spectacular supernova explosion, where the outer layers of the star are ejected into space, leaving behind a dense core that becomes a black hole. Their immense gravity warps the fabric of space-time, creating a singularity, a point of infinite density. At this singularity, the known laws of physics break down, and our understanding of the universe is challenged. Black holes come in different sizes. They can range from small, stellar mass black holes to the colossal supermassive black holes found at the centers of galaxies. Stellar mass black holes are a few times more massive than our Sun. These are typically formed from the remnants of massive stars that have undergone supernova explosions. Supermassive black holes, on the other hand, can be millions or even billions of times more massive than the Sun. These giants are found at the heart of most galaxies, including our own Milky Way. These behemoths reside at the centers of galaxies, including our own Milky Way. Their presence influences the motion of stars and gas within the galaxy, playing a crucial role in its overall structure and dynamics. Black holes play a crucial role in the evolution of galaxies. They can regulate star formation and affect the distribution of matter, shaping the galaxy over billions of years. They influence star formation and the distribution of matter. The intense gravitational pull of a black hole can trigger the formation of new stars or disrupt existing ones depending on the circumstances. Studying black holes provides insights into the fundamental laws of physics and the nature of gravity. Researchers use advanced telescopes and simulations to explore these mysterious objects and their effects on the universe. Their existence challenges our understanding of space, time, and the very fabric of reality. As we continue to study black holes, we uncover more about the universe's most profound mysteries and the limits of our knowledge. In the immediate aftermath of the Big Bang, the universe was a chaotic and energetic soup of particles. This primordial state was a seething mass of energy and matter where the fundamental forces of nature were just beginning to take shape. The universe was incredibly hot and dense, a place where particles collided with unimaginable force, creating a turbulent and dynamic environment. Within this primordial soup, tiny fluctuations in density may have given rise to a particularly intriguing type of black hole. Primordial black holes. These density fluctuations were like ripples in a pond, but on a cosmic scale. They were the seeds from which galaxies, stars, and black holes would eventually grow. In some regions, the density was just right for gravity to take over and compress matter into incredibly dense objects. Unlike their stellar mass counterparts, primordial black holes did not form from the collapse of stars. Stellar black holes are born from the death of massive stars, which explode in supernova and leave behind a dense core. Primordial black holes, on the other hand, were born in the very early universe, long before stars even existed. Instead, they were born from the extreme conditions of the early universe. The intense energy and density of this period created the perfect conditions for these black holes to form. The early universe was a place of extremes where the laws of physics as we know them were pushed to their limits. Primordial black holes could span a vast range of masses. They could be incredibly small, with masses less than that of a mountain, or they could be enormous, rivaling the mass of entire galaxies. This wide range of possible masses makes them unique among black holes. Some might be as light as a small asteroid weighing only a few tons. These tiny black holes would be incredibly difficult to detect, as they would emit very little radiation and have a very small gravitational influence, while others could be billions of times heavier than the Sun. These massive primordial black holes would have a significant impact on their surroundings, influencing the formation and evolution of galaxies. This incredible diversity in size makes primordial black holes a compelling target for astronomers and physicists alike. Studying them could provide insights into the conditions of the early universe and the processes that shaped its evolution. Researchers are particularly interested in understanding how these black holes formed and what role they might play in the cosmos today. One of the most intriguing aspects of primordial black holes is their potential connection to dark matter. Dark matter is one of the greatest mysteries in modern astrophysics. It is an invisible substance that does not emit, absorb, or reflect light, making it incredibly difficult to detect directly. Dark matter is an invisible substance that makes up a significant portion of the universe's mass. Despite its elusive nature, we know it exists because of its gravitational effects on visible matter. It acts like a cosmic glue, holding galaxies and galaxy clusters together. Its gravitational influence is evident in the motions of galaxies and galaxy clusters, which move in ways that cannot be explained by the visible matter alone. The presence of dark matter is inferred from these gravitational effects, which suggest that there is much more mass in the universe than we can see. But its true nature remains a mystery. Understanding primordial black holes could potentially unlock some of the secrets of dark matter, providing a new window into the fundamental workings of the universe. Dark matter doesn't interact with light, making it invisible to our telescopes. We can only infer its presence through its gravitational effects. Scientists have proposed various candidates for dark matter, and primordial black holes are among the contenders. If primordial black holes exist in sufficient numbers and with the right mass range, they could account for the observed dark matter in the universe. Their gravitational pull could explain the anomalous rotation of galaxies and the clumping of matter on large scales. However, the search for primordial black holes as dark matter remains a challenge. Section 4. Seeking the invisible. The challenges of detecting primordial black holes. Detecting PBHs is a formidable task. They are incredibly faint and difficult to distinguish from other astronomical objects. Unlike stellar mass black holes, which can be detected through their interactions with companion stars, PBHs are thought to be isolated wanderers in the vastness of space. Despite the challenges, scientists have devised several methods to search for PBHs. One approach is to look for their gravitational effects on light. As a PBH passes in front of a distant star, its gravity bends the star's light, causing it to brighten momentarily. This phenomenon, known as gravitational microlensing, can reveal the presence of otherwise invisible objects like PBHs. Section 5. Cosmic capture. Asteroids ensnaring black holes. Another intriguing idea is that PBHs could be captured by asteroids, leading to fascinating cosmic interactions. If a PBH were to pass close enough to an asteroid, the asteroid's gravity could pull the PBH into orbit around it. Over time, the PBH's gravity could have a profound effect on the asteroid's structure, altering it significantly. As the PBH orbits the asteroid, it would gradually consume material from the asteroid's interior, changing its composition. This process could create a hollowed-out asteroid with a PBH at its center, a truly unique phenomenon. Such objects, if they exist, would be incredibly difficult to detect with current technology. Section 6. A new discovery unveiling a stellar mass black hole. While the search for PBHs continues, astronomers have made significant strides in detecting and characterizing stellar mass black holes. Recently, a team of astronomers announced the discovery of a black hole with a mass of approximately 3.14 times that of the Sun. This discovery is particularly noteworthy because it falls within a mass range that was previously poorly understood. The black hole was discovered through its interaction with a companion star, a red giant located about 5,800 light-years from Earth. The black hole's gravity pulls material from the red giant, forming an accretion disk of hot gas around the black hole. This accretion disk emits X-rays, which were detected by astronomers. Section 7. The curious case of the wide orbit unveiling the black hole's past. What makes this discovery even more intriguing is the black hole's unusual orbit. Unlike most black holes that are found in close binary systems, this one defies the norm. It orbits its companion star at a remarkably large distance, completing one orbit every 83 days. This is quite unusual because most black holes in binary systems have much shorter orbital periods. This wide, near-circular orbit suggests that the black hole may have formed through a different mechanism than most other known stellar mass black holes. Typically, black holes are formed from the remnants of massive stars that have undergone supernova explosions. One possibility is that the black hole was once part of a triple star system. In such a system, complex gravitational interactions can occur, leading to the ejection of one of the stars or the black hole itself. Interactions between the three stars could have ejected the black hole into its current wide orbit. This scenario is fascinating because it suggests that the black hole's past was much more dynamic and chaotic than previously thought. Another possibility is that the black hole formed through an asymmetric supernova explosion, in which the exploding star's core received a kick in one direction, propelling the newly formed black hole into a wide orbit. This kind of supernova explosion is rare, but can result in the black hole being flung far from its original position. Understanding the formation and evolution of such black holes can provide valuable insights into the dynamics of stellar systems and the life cycles of massive stars. It also challenges our current models and theories, pushing the boundaries of what we know about the universe. As we continue to study these enigmatic objects, each discovery brings us closer to unraveling the mysteries of the cosmos. The curious case of this wide-orbit black hole is just one piece of the puzzle, but it is a crucial one that could reshape our understanding of black hole formation and behavior.